So our slist class now has these new fancy methods, size and add last. But there's some issues. Both of them are pretty slow, and we're going to focus on the size method in this particular lecture and discuss how to make it more efficient. So how slow is size? Well, to maybe bring this to the form and make you think about it in the following way. Let's suppose size takes 2 seconds to process a list of size 1000. That is, size, which steps through the list one item at a time until it finally reaches the end, is going to take 1000 seconds. Now, you don't really know exactly how a computer works, but just using your intuition, how long do you think it will take on a list of size 1,000,000? So ponder that for a moment. So I say the answer is 2000 seconds. That if I have a list that's 1000 times as large, then whatever the computer is doing inside, and it's to step through the list, it's going to have to do that 1000 times as many times, so it should take 1000 times as many seconds, for a total of 2000. So the more interesting question is, how do we fix that? And so I'm going to leave this as a puzzle for you that I'd really like you to ponder, to figure out a way to make size really fast, no matter how big the list is. I don't care if there's 1 billion items, I want it quick. So think about how you might do that. And I will wait here patiently. Okay. So what I propose is that we, instead of calculating the size on the fly every time size is called, which could take a long time, we're going to set aside some information about the size up front. So I'm going to have private int size, and that's going to represent the current amount of information in the data structure. So what's the size of a S list with one item? 1. What should I do whenever I add an item to what should change about the size? Size plus equals 1. What about get first? Should the size change? No. Add last. Indeed, we will add 1 to the size. I'll do it at the front. Doesn't matter where. So that is all we need for the size to be updated. And so now we come to the size method. Well, now rather than calculate, I'm going to delete all this beautiful code we just spent so much effort discussing. This code that speaks the secret language of the gods is going to be buried beneath the earth. And instead, we're going to return size. It's pretty typical, right? Like when you write a book of arcane evil from ancient gods or whatever, usually once you're done with it, you discard it to be discovered later at some day to destroy civilization. So we'll just say that's what we're doing. But we'll find that in later parts of this class and in the projects, you will actually be using that pattern of having the secret language of the gods. But here it's actually easier for us to just compute the size up front and return it whenever we're ready for it. So now when we print out the size, we still get 4, but it doesn't matter how big the list is, this will be very fast. We did it. Okay. So to debrief, basically what we just did is we maintained a special size variable that caches the size of the list. So anytime the size of the list changes, we update it. And caching is just a fancy term for putting aside some data to speed up retrieval at some later date. It is redundant, but it also speeds us up. Now, it doesn't come for free. There's this old saying that there ain't no such thing as a free lunch. We did have to do some work. What we changed is that every time the size of the list is modified, we have to tweak the size a little bit. But it doesn't really have a meaningful impact on our performance, and for any practical circumstance that I can imagine, spreading that work of calculating the size over each add call, to me, is a net win in almost any case I can even imagine. Let's look at a visual that compares our naked recursive data structure with our S-list in the context of caching. So before we said S-lists have this nice advantage that whenever you want to manipulate the data or see the data, you have to go through this middleman. This middleman provides you with very easy to understand methods that are guaranteed safe and avoid you from shooting yourself in the foot in various ways. Now, another nice advantage of the S-list structure to have this middleman is that it serves as a natural place to store meta information about the entire list. So for example, we can store the size of the list here. It is technically redundant. You can compute the size without this variable, but it speeds up the computation of size because you just need to return this value. You could also store other things here, right? Like you could store like the maximum or the minimum or the largest value that was ever put in there, and those would also work. By contrast, with a naked recursive list, it's not so easy. You could, in principle, do something like cache the size inside of each node, but even then, that means that anytime you change something in the list, you have to update a bunch of size variables. You could also, for example, somehow, if you had a language that allows it, bind a variable up here that tracks the size of the whole thing. But in Java, there's no natural facility to do that. So in effect, what you'll end up doing is having multiple variables that you have to keep straight. Here, this object-oriented programming approach means that we let the object control everything. We tell the object, your job is to not only do all of these tasks, but also to track the size for me. And in that way, it's just a natural way to organize our code. So again, the int list can do all the stuff that an S list can do, but an S list is going to be a more natural approach in nearly every way.